Okay, the next real basic type of force problems are called Atwood machines. They're essentially just involving pulleys. It's a series of pulleys. You're probably not going to get more than one pulley on a system, but there could be potentially more. But in any case, an Atwood machine, I'll give you a basic example that would look like this. So what we have here is two masses. Okay, so there's a mass with a massless string. Of course, all our strings are massless, hung over a pulley, and another mass over here. I'm going to give this thing friction, so we'll just say that mu is not equal to 0. So there is a force of friction here. Now, what we have to do is identify the forces acting on here. So I'm just going to do that in a different color here, and just say that for this one here, that there's a force of gravity pulling down. Okay, that should be force of gravity pulling down on this. A little messy. Force of gravity pulling down, which will be equal to mg, and I'm writing capital Mg for that one. Okay, so there's your force of gravity pulling down. What is also acting on this object alone will be the force of tension in this rope right here. So I'm going to just write that that's Ft. Okay, so there's a force of tension pulling up and a force of gravity pulling down. What also is acting on this rope, on this mass? On this mass, you're going to have a force of tension from that, Ft. Now, in fact, I can call these both exactly the same force of tension because it's the same rope. Our ropes are massless, and in fact the force of tension will just continue all the way through here, so that this will be the same force of tension pulling this object to the right as this force of tension is acting up. Okay, exactly the same force. In addition here, let's see, we have what else is acting here? Well, there's going to be a force of gravity on this guy, and that's equal to lowercase mg. There's going to be a force normal acting up. In fact, these two will be exactly the same because we're assuming here that this object is not going to be accelerating up or down. And there'll be also a force of friction acting on this way, and that'll be mu Fn. Okay, and Fn in fact will be equal to mg. So you'll start seeing some things equate here. Looking at this diagram here, you can do a number of things. You could solve for the total acceleration. Well, if we wanted to know the acceleration of this setup here, okay, what we're going to get is I'm going to call, it's awkward, but I'm going to call clockwise, in this case clockwise, I'm going to call this direction here, I'm going to call that positive, and counterclockwise I'd call negative. Okay, so anything moving clockwise is positive, to the counterclockwise will be negative. Looking at this one here, what we have is a couple of things. In this tug-of-war here, we have really, on this object right here, okay, if we're only dealing with this object, on that object right there, what we have is we have that the net force will be equal to, pardon me, let's write that again. The net force will be equal to big mg minus Ft. Okay, and that will equal all this divided by the mass. Okay, the mass will be equal to its acceleration. And that'll be its mass. Okay, so that'll be mg minus Ft will equal the acceleration of big M. Okay, the acceleration of big M. The other one right here, okay, will be, well, let's take a look at its forces. Now, the vertical forces cancel, but the other one right here, this one, okay, this one here will be, let's see here, the net force will be equal to force of tension minus force of friction. And of course, that's all divided by mass if I want to know the acceleration on little m. Okay, so there's the acceleration on little m. If you take a look at this acceleration of big M and the acceleration of little m, in fact, these are exactly the same accelerations. They have to be. Okay, they have to be the same acceleration. The reason being is because this object will all move together at once. Okay, it'll all move together. So in fact, AM will equal, this will equal a big M. You can move around and start solving various things. There are other ways to do this question. If they just ask you strictly for the acceleration, you could get here that, well, M, let's see here, what we could do is say, well, this is really looking like this. Okay, there's a lot of ways to analyze this, but really this is what this drawing looks like. There's a force of gravity pulling this way on this giant object. Okay, there's a force of gravity pulling this. What's pulling it back? The only thing pulling it back really is force of friction. In fact, if I figure out the force of gravity of this object, that's the force of gravity on big M. So really what this thing would look like is it's pulling this way and pulling back. Okay, that's the tug of war here. We don't worry about the force of tensions because again, they're equal and opposite. They just kind of cancel each other out. So the net force here, you could argue on this entire object, okay, would be equal to the force of gravity on big M minus the force of friction on little m. Okay, there's your net force. Of course, we would divide this by the mass. Now, the mass in this case is the whole system, which would be m plus m. Kind of awkward to see, but in fact, this equation, okay, sorry, this should be the mass total. This will give you the acceleration of both blocks. And in fact, this acceleration will be the same as that one, and it'll be the same as little m. They are all the same. A little awkward to see, but they'll all be the same. This is working through a complicated scenario in terms of Atwood machines. Let's take a look at how to make this even more complicated. What we could throw at you is basically an inclined plane. And the only thing that they'll do is they'll have a pulley up top, in which case they'll have maybe a mass here, call it big M, and a little mass here. Nothing really changes. Again, clockwise will make positive, counter, negative. The only difference is that here you'll have a component of gravity on this one, call it force parallel, as well as a force of friction if it's accelerating clockwise. Again, if it's accelerating counterclockwise, if let's say this was actually much larger than this, and it was accelerating this way, then the force of friction would actually be going up. So you have to watch out for your signs. You'd have to decide who's bigger. But I'm going to assume that this is larger, which is why force of friction is down. Again, your force normal is here. Your force perpendicular is there. And this is going to have your force of gravity. Again, you could work through and say, well, force of gravity minus these two forces will equal my net force. That's one way to look at it. Once you get the acceleration of an object, you can easily find these forces of tension though. Okay, once you have the acceleration, and I can go through it the same way, I'm just going to find the acceleration of this whole system. It will be equal to force of gravity on M, okay, on this object, minus force of friction minus force parallel. These two are in the negative direction according to my diagram. I'm going to divide that all by the total mass. That's how I would get the acceleration. Once I know this acceleration, okay, and calculating it all out, once I know this acceleration, I can take this and plug it into this. So once I know, let's say it's accelerating down, which is according to my diagram, that's the way it's accelerating. If I know it's accelerating down, what I can do is take this acceleration and say, well, what's the net force only on this object? You can isolate it. Before I did the system, now I'm doing the object. And the net force on this object right here, okay, will be equal to M, big M, times A. In which case, A is what we figured out down here. So it's complicated, but you could figure out the acceleration, then figure out the total mass, and find out what the net force is. Why is that useful? Because the net force is also equal to the force of gravity on big M minus your force of tension. And once I have net force, I can get your force of gravity minus your force of tension. I can get force of tension. And you could do it similarly with this block as well by finding the net force only on that object. Okay, there are a variety of ways to do that. This is essentially an Atwood machine. There's a variety. There's various forms of this. Sometimes you'll get ones that are just a pulley up here and a mass here and another mass here. Okay, there's a variety of forms. They all do essentially the same thing. Again, the force of tension gets transferred throughout the entire string because all of ours are massless, and you can figure out the total force. Be careful of a couple things in terms of the total mass. Using when to use the total mass is when you're looking at the system. Use individual masses when you're looking at only the individual object itself.